Okay, this is the title of my presentation. It's on the solution of a fractional extension of Higgs boson equation into the de Sitter spacetime. My name is Hector Vargas Rodriguez, and I'm from the University of Guadalajara. Okay, so this is the schedule of my presentation. So first of all, I'm going to give a small background on the problem. I'm going to talk about the numerical methodology. So I'm going to talk then about some numerical properties of the numerical methodology, and I'm going to provide some computer simulations. Okay, so about the background. Okay, so the motivation of this talk is this equation, which is here. So this is a hyperbolic model. So this is actually the Higgs boson equation in the de Sitter spacetime. You can see that this is a diffusion equation, which has a non-constant diffusion in front of this term, and this is the derivative of the potential function. We're going to consider initial and boundary conditions. P is going to represent the number of dimensions. Okay. So there are various reports about the solution, the existence of solutions of Higgs boson equation in the de Sitter spacetime. Unfortunately, most of these results are qualitative results, so they don't provide conditions under which the solutions do exist and are unique. This topic is a very hot topic of investigation recently, as is the analytical investigation of the solutions of this model. Okay, so in this work, we're going to consider a fractional extension of the Higgs boson equation into the de Sitter spacetime. So the fractional derivatives are going to be understood in the sense of Riest's. This is the definition of the Riest's fractional derivative of function phi of order alpha. And we are going to define the fractional Laplacian in this form, which is an extension of the usual Laplacian, and also the gradient, the fractional gradient, is going to be defined as this vector, which extends a definition of the usual gradient. Okay, so we are going to consider a box in the p-dimensional space. Omega is going to be our space-time definition, and this is going to be the extension of the Higgs boson equation in the de Sitter space-time that we're going to consider in this case. So notice that the only difference lies, first of all, in the generalization of this coefficient, in that we are using fractional derivatives, fractional Laplacian, and we are going to consider the derivative of a general potential function, f. We are going to consider initial and boundary conditions. Okay, so as I said, this is the general time-dependent diffusion coefficient. So this is the fractional diffusion, and this is the generalized potential. Okay, we are going to introduce some notations. So this is the inner product. So this is usually understood in this way, and the function, the system that we consider in this talk has some energy associated. So this is the energy associated to our system. The energy density is just going to be the integrand in this expression, which is going to be given in this form. Okay, and we have this corollary that states that the derivative of the energy with respect to time is given in this form. How do we obtain this expression? We just take the derivative of the terms in the energy. So remember that the energy is given in this form, so we take derivatives of all the terms. So we take the derivative of this term, which gives you this expression. We remember that this property is satisfied, therefore we obtain also this formula, okay, and this other formula also. Now for this term, so the derivative is going to be given in this form. Okay. Finally, we collect terms, we put them together, and we obtain this expression, okay, which reduces to this one, and so on. We introduce more terms, and finally we reach what we wanted. So about the numerical methodology, so we're going to use a finite difference discretization of this model. Okay, so we are going to divide the spatial coordinates in a finite number of equally spaced subintervals, as same thing as for the time. these are going to be some linear operators that we're going to use. So they are all traditional operators. We're going to define inner products, norms, and we are going to introduce this traditional nonlinear operator to approximate the derivative of f with respect to phi. Okay. Recall the concept of fractional center differences, which was introduced some years ago by Otigata. If you have a function f, so the fractional center difference of f of order alpha at x is this double series where the coefficients are given in this form. And the coefficients satisfy various interesting properties which are going to be useful. So here I'm going to plot some values of the coefficients for certain values of alpha. So this is for alpha equal to 1, alpha equal to 1.5, alpha equal to 2. Okay. This is our definition of discrete Riest's fractional partial derivative. So this is an approximation. Okay. So this is the way we're going to approximate the Laplacian. This is the way we're going to approximate the gradient operator. So we're going to suppose that phi and phi0 and phi1 are sufficiently smooth functions, and the numerical method to approximate the solutions of the continuous model is going to be given by this expression. Okay. It's easy to see that this is a three-step implicit finite difference model. Okay. So if we see the stencil is provided in this way. So these are the unknowns, and these are known approximations. Okay. We also introduce some discrete forms of the Hamiltonian and the energy functionals, which are given in this way. And we have this theorem for the discrete rate of change of energy with respect to time. Okay, so the discrete rate of change of the energy is going to be given in this form. Okay, I'm going to skip the proof. The proof is relatively long, though standard. We're going to talk about the structural properties. The first one is solvability of the system. So under suitable conditions and when tau is sufficiently small, the model, the discrete model, is going to be solvable for any set of initial conditions. Now, the way to do this is following by induction. So these first approximations are given. And supposing that these approximations have been already calculated, then we have to prove that the solution at the time k+1 can be obtained. Okay, so in order to do that, we consider this system in which the unknowns are the solutions at the time k+1. Okay, and we are going to use Brouwer's fixed point theorem. Okay, so following this idea, we take the inner product with respect to psi. So these are the inner products. We bound from below, okay, using Young's inequality. Okay, we continue bounding from below. Okay, so we use the condition of smoothness of the function f. Okay, we introduce some notation. Okay, and we finally obtain that this expression is bounded from below by this, where lambda is given in this form. So this lambda is greater than 0. And notice that if this condition is satisfied, then this inner product is greater than 0. And Brouwer's fixed point theorem guarantees that there is a solution for the system. Okay. About the consistency of the model. Okay, so we need to suppose that f, lowercase f, and capital F are differentiable functions, and that phi is a sufficiently smooth function. So it's of this class of function. Then there are constants c and c prime, which are greater than 0, which are independent of tau and h, such that the difference between the continuous operator and the discrete operator is bounded by this quantity. Okay. Now the way to do that is by using the triangle's inequality. So we do first a substitution, then we use the triangle inequality, then we use smoothness of the solution phi. Okay. So we bound all of these terms conveniently, and finally, we obtain using the mean value theorem and Taylor's theorem that this bound is satisfied. Some similar argument applies for this other inequality. Okay, For this other inequality, we'll also start off by taking the absolute value of the difference. Okay, we substitute, we use the triangle inequality, we bound terms, okay, and finally we reach that inequality. Okay. Okay. For stability, okay, to prove stability, we're going to use a discrete form of Cronwell's inequality. So this is the discrete form that we're going to use. This lemma was proved by Pen-Yu in 1977. Okay, and stability tells us that, well, basically this is stability. So this is omega k. Omega k is this quantity, which is the solution, depends on the solution at time k, and rho depends on the solution at time 0. So as you can see, the omega k's are going to be bounded by this quantity, which depends on the solution at time 0 times this constant. So this is going to assure stability provided that this condition is satisfied. Tau sufficiently small. Okay. Okay. As one of the corollaries, we obtain uniqueness of solutions. So under the same conditions, given any two solutions of the same problem, they have to be the same. Okay. This is an easy consequence of the previous theorem. And also we have a convergence of the system. So if f is sufficiently regular, if lowercase f is also sufficiently regular, and if phi is also sufficiently smooth, then the solutions of the numerical model converge to the solutions of the continuous model with quadratic order of convergence, as I say here, in the L2 norm. Okay, the proof, as I mentioned before, is very similar to the proof of stability, and we are going to omit those proofs because they are very long. Okay. We're going to provide some simulations. So to that end, we're going to remember some qualitative results available in the literature. It's well known that the Higgs boson equation has some solutions which are bubbles. Okay, so we are going to examine the presence of bubbles also in the fractional case. And we are going to introduce these functions to that end. So these functions are like bubbles. Okay. So we are going to consider the continuous system in the usual Higgs boson equation with the de Sitter spacetime, and these are going to be the values of the parameters. This is gamma, this is q, this is lambda, and this is mu. Okay. So we're going to restrict our attention in this case to the example when b is the interval that goes from -1 to 2, and capital T is equal to 0.03. So computationally, we're going to take h to be 0.01, and tau is going to be this number, and we're going to provide these initial conditions. This phi is going to go to the previous case, previous page, so it's this expression, okay, and phi1, the velocity, is equal to 0, okay. We must point out here again that the presence of one-dimensional bubbles has been predicted in the literature previously when alpha is equal to 2. Okay, that's in the non-fractional case. Okay, so these are some solutions. So this is the evolution of some bubble. Okay, this is space and this is time for various values of alpha, 1.6, 1.8, and 2. Okay, so these are the evolutions of the bubbles, and this, in this case, are the Hamiltonians. So the solutions are first row, Hamiltonians are second row. Okay. We considered the same problem, now taking different initial conditions, 0 initial velocity again. Okay. We take different alphas. These are the solutions, and these are the Hamiltonians. Okay. It's important to mention that the implementation of this model has been carried out using Fortran because the simulations are computationally intense. And we have used some of these references which are available in the literature. This is a very important first effort to try to produce Hamiltonian systems to simulate the Higgs boson equation in the de Sitter spacetime. And this is also some recent progress using the radially symmetric assumption and the solutions of Higgs boson equation. There are more references here, so this is also something important. So this is the way we are approximating the fractional derivative. So we use Ortigata's perspective. Okay, more references. That's it. Thank you all.